Hi, this is Jack Jackson again, and this is part 3 of our series of lectures on continuous distributions. Today we're going to be talking about the triangular distribution. And as the name suggests, we're going to see a triangle in this distribution. That's going to be the shape that we see beneath the PDF graph and between that and the x-axis. So we're going to see a triangle, which of course is going to have area 1. So basically, let's think back to a uniform distribution first. In uniform distribution, we had a graph that has 0 outside an interval a to b, and it's a constant function between. In a triangular distribution, we're also again going to have an interval from a to b that outside of it there's the PDF has a value of 0. So basically the only thing that really matters is between a and b. But this time, instead of a horizontal line segment, we're going to get a slanted line segment, or possibly 2 line segments to make up the top of a triangle. Now remember in general that if we have a descriptive statistics, the data value that occurs the most often is called the mode. When we get to a discrete distribution, the mode is then the one with the highest probability, that is the input value with the highest probability, which will be the highest bar on the graph of the PDF. Of course, probabilities are kind of like relative frequencies, so that's very comparable to the mode in the descriptive statistics example. Now, when you get to a continuous distribution, the mode is the value for the input, value of the random variable, the x, such that the curve on the PDF graph is at the highest point. So once again, it's the highest point on the curve like it was in the PDF of a discrete distribution, but in a continuous distribution, of course, that's not a probability, but it's still the highest value. So to specify a particular triangular distribution, we could give it parameters a, b, and m. A and b are the 2 endpoints, so that if it's less than a or bigger than b, the 0 probability outside of that interval. And the m is some number between a and b. It could be all the way at one end or the other or somewhere in between, and that's the value of the mode. So let's take a look at a graph of one of these. So here you see a graph, and actually this is a little bit deceiving because this red vertical line really is not part of the graph. It actually comes across at 0, goes up a straight line, and then like the uniform, it has a break there, and it drops down to 0 from there on out. This one's triangular 3, 7, 7, so the mode is all the way to one end at x equals 7, so the shape we end up getting there is a right triangle. So a is 3 and b is 7, so between 3 and 7 we're using the graph of the PDF as this linear thing here. So here's some basic questions about this. Looking at the picture, use what you know about areas of triangles, linear functions, and so forth, to see if we can come up with a few things about this distribution. So in particular, what's the length of the base of the triangle? What is the length of the base of a triangle in general, triangular ABM? And what's the height of this triangle? And in general, what's the height of the triangle in general for triangular ABM? Take a minute or two and figure this out, and then come back and check it in a minute. Press pause now. No, really, press pause now and figure this out, and then come back. Well, the base here is from a to b, so that length is just b minus a. So in that case, 7 minus 3 is 4. So you can see this is 1, 2, 3, 4. Yeah, it's 4 units across the base here. Now what's the height of the triangle? Well, to do that we need to go backwards from finding the area. So the area we know is the area of that triangle, which of course is 1 because that's the entire probability. The entire probability area between is an area between a PDF graph and the x-axis, and that total area has to be 1. So we know the area of the triangle is 1. We also know the area of a triangle is 1/2 its base times its height. And the base, we already figured it out, is b minus a. We can solve this for the height. Multiply both sides of that equation by 2, and divide both sides of the equation by b minus a, and we get the height is 2 over b minus a, or in this case 2 over 4, or 1/2. And so we know the coordinates of that point at the very top, that maximum point, are m, comma, 2 over b minus a. So in this case 7, comma, 1/2. Notice, by the way, that the scale is not a square scale. These areas are usually very small. I mean, the total area is only going to be 1 on any of the probability density functions. So oftentimes they're not very tall. Like this one only goes up to 1/2. So we usually expand out the vertical scale a little bit to be able to see it just a little bit better. Okay, so use this information and see if you can figure out actually a couple of different things. We want to figure out these probabilities: the probability that x is less than 4, the probability that x is greater than 4, the probability that x is greater than 5, the probability that x is between 4 and 6, and then also what's the formula for the PDF. So see if we can go back and figure out those two things: the formula for the PDF and the values of these probabilities. Figure these out now, please. Press pause. Well, figuring out these probabilities is just figuring out areas under this graph. And luckily the shapes are triangles, and so triangles are not too hard to find the areas of them. We might come up with some areas of triangles or possibly some right trapezoids, but again, not too hard to find those areas. But it might be useful for us first to find out the formula for this line segment here. Now remember, in general, that we have a line. It has a formula: y equals m times parentheses x minus the root, or the x-intercept, okay, which is a in this case. So we just have the slope times x minus a. Well, what is the slope here? Its slope is delta y over delta x. Delta y is the height here, which we already figured out is 1/2, divided by the base here, which we figured out is b minus a, which is 4. And so the slope is 0.5 over 4. That in fraction form is 1/8, or 0.125 in decimals. And since the x-intercept is 3, 0, this has the formula y equals 0.125 times parentheses x minus 3. And so that is the appropriate formula between 3 and 7. And outside of that, of course, it's 0. That formula is what we might call a factored form, or a slope x-intercept form, or a slope root form. Now use that to help us compute these probabilities. So if you haven't done these probabilities already, go ahead and stop this and figure them out again. If you've got all the answers for them, then go ahead and go on. Press pause now. Okay, so let's take a look at these. The first one, we're taking the probability that x is less than 4. We want to compute that probability. So what we're doing is we're finding the area of this little shaded triangle that you see in that first example. And so we're looking at between 3 and 4. So the probability that x is less than 4 turns out to be really the probability that x is between 3 and 4, because there is no probability less than a, which is 3. So we really just need to do from 3 to 4. That gives us a base of 4 minus 3 is 1. It gives us a height of, well, it's just going to be the y value of the PDF at that point. That's why it was useful to go back here and figure out this formula right here first. I can plug in the x value I'm interested in here to find heights on that curve, or y values on that slanted line there. So in this case, x is 4, so we just plug that in there. And 4 minus 3 is 1 times 1.125. And so 0.125, or 1/8, is the height right there. The height right there. And this is 1/2 base times height. So it's 1/2 times 1 times 0.125. That's 0.0625. And that's the area of that triangle, and that's the probability that x is less than 4. Now what if we want to find the probability that x is greater than 4? Well, again, it cannot go past that interval from A to B, so it can't go past B of 7. So when we're finding the probability that x is greater than 4, what we're really doing is find the probability that x is between 4 and 7, which gives us an area in the shape of this right trapezoid here. Now we can figure the area of a right trapezoid. It's not too difficult, but it's easier just to figure the area of a triangle. So I'm going to do this with just areas of triangles. I know that the area of the big triangle is 1, and if I subtract off the area of the little triangle, I get what's left. So it's just 1 minus the probability that x is less than 4, and we just figured that out to be 0.0625. 1 minus 0.0625 is 0.9375, which is the shaded area there in the second example. In the next example, we're doing x is greater than 5, which is, again, since you can't really go past 7, that's really just the probability that x is between 5 and 7, which is the area of that right trapezoid. Now again, I could figure that out directly, but it's a little bit easier if we just take 1 minus the area of that triangle. So it's 1 minus the area of the unshaded triangle here, which is 1/2 base times height. And the base is 5 minus 3. 5 minus 3 is 2. And the height is 0.125 times, well, what's the height? It's right at this end, 5 minus 3, which of course is 2 times that is 0.25. So the height here is 0.25. The base is 2. The 1/2 is from the formula. And so we get 0.25 when we multiply those together. 1 minus that is 0.75. Now what about between 4 and 6? Now again, there are a couple different ways of doing this. When we're talking about the probability that x is between 4 and 6, we're computing an area of this, let's see, it's a right trapezoid. Now we can do that directly, or I can think of it as two triangles. A triangle that goes all the way from 3 to 6, and then subtract off the triangle that goes from 3 to 4. So I'm going to do it that way. Not the only way to do it, but I think perhaps the easiest for most of you. So we're going to look at this and see that the probability that x is less than 6 is really this area from 3 to 6 in that triangle. So from this point at A to 6 up to this point here above 6. And so that's 1/2 base times height. That's 1/2. 6 minus 3 is the base, or 3 is the base. And the height over here at the end is 0.125 times 6 minus 3. And that is 0.375 as the height. So multiply all these together and you get 0.5625. Now that's the area of a triangle going all the way from back to the A point here. We have to subtract off this unshaded triangle and we'd be left with the brown area that we're looking for. So the unshaded triangle right here to the left from A equals 3 to 4 is 1/2 base, 4 minus 3, times height, which is 0.125 times 4 minus 3. Alright, that's 0.125 for the height here. Base is 1, 1/2 is in the formula. Multiply those together, you get 0.0625, and that's what we're subtracting from 0.5625, and we get exactly 1/2. So that shaded area is exactly 1/2 of the area of the total triangle, which is in area 1. So that is an area of 1/2. So the probability that x would fall between 4 and 6 is 1/2. Now, in general, we have a triangular distribution ABM. Now, M doesn't have to be all the way to the end to be the same as B, or all the way to the A, where we have a right triangle with a right angle down on the x-axis. M could be something in between, like this example. So what are the coordinates of that maximum point in general for this distribution? We need x and y coordinates of this point right here at the very top. What are they? Figure it out now. Press pause. Okay, well we're back. We know that the length of the base along the x-axis is always b minus a and the total area is 1. And just as we figured this out before, the height is 2 over b minus a, and the height that's the maximum height right at the mode. So it's going to be m, comma, 2 over b minus a is going to be the coordinates, ordered pair coordinates of that maximum point. So now we have a triangular distribution 2, 6, 5. That is, a is 2, b is 6, m is 5. Write down the formula and draw the graph of the PDF for this distribution. It may take a minute or two, but please go do this. It's very important that when I ask you to pause these videos, that you do so, do the work yourself, and come back and watch it again. Please press pause now. Okay, so let's take a look at what we've got. In general, the height of the PDF at the mode is 2 over b minus a, so the maximum height is 2 over 6 minus 2, so that's 2 over 4, 1/2. So the maximum point is 5, 1/2. That's going to be the coordinates of that top point. And the graph is given below, so that means you have a slope of 1/2 over, well, let's see, going from 2 to 5 is a delta x of 3, and a height of 1/2. So you got 1/2 over 3 is 1/6, so that's the slope of the first one, and it goes through the point 2, 0, so it's 1/6 times x minus 2. And that'll be true for this increasing side of the top of the triangle, and that is x value going from 2 to 5. However, if you look at from 5 to 6 for x, that's on a different line, a line that's going down. Different slope, different line. Goes through the different point on the x-axis as well. It goes through the point B, that is 6. So it goes through 0, 6. No, excuse me, 6, 0 on the x-axis. And so that would be x minus 6 would be their factor. And then the coefficient out front is just the slope. In this case, it's going to be a negative slope because it is going down as you go right to left. And if you look, we're dropping how much? Well, the height there is 1/2. So we're dropping 1/2. And we're dividing that by the delta x. And the delta x is, well, it's just 1. So the slope is negative 1/2. And so our formula is negative 1/2 times x minus 6. And that works for x's between 5 and 6. If x is less than 2 or greater than 5, I'm sorry, that should say 6. I'll fix that on the slide. As 0, the slash one should say 0 for x is greater than 6. So if it's outside the AB, less than 2 or greater than 6, then the y value is 0. Fix that before I print it out for you. So, here's some of the information worked out. The height of the triangle, the base of the triangle, the mode, the formula for the PDF, decimal approximations of those two slopes, and the graph. So, for this particular distribution, this is the same one. Compute and illustrate the following probabilities. Probability that x is less than 4, probability x is greater than 5, and probability that x is between 3.5 and 5.5. Please press pause now to do this. Okay, well, we're back. Let's look at this first one. Probability that x is less than 4 really is the probability that x is between 2 and 4, because there is nothing less than 2 that's going to give you any probabilities out there. Zero probability out that way. So we're finding the area of this little shaded triangle. That area is 1/2 its base times its height. 1/2 is there. The base is, however long that is, 4 minus 2, which is 2 for the base. The height is 1/6 times 4 minus 2, which is 1/3. 1/2 times 2 times 1/3 is 1/3. So that area is 1/3, or 0.3 repeating. Probability that x is greater than 5. Well, we're looking at between 5 and 6. Notice that entire piece is on that descending side, And so that's just a triangle again, but one where the slope is decreasing on the top edge there. So it's just 1/2 base times height again. Base is 6 minus 5, or just 1, and the height is negative 1/2 times 5 minus 6, which is positive 1/2. Okay, multiply those together, and you get 1/2 times 1 times 1/2 is 1/4. And so that area is 1/4, or 0.25, for that area, which is the probability we're looking for. Okay, finally, I think we had one more exercise, and that was to find the probability that x is between 3.5 and 5.5. And if you draw this out, you get this, well, it's actually a pentagon, but it's made up out of two trapezoids, two right trapezoids. However, it's probably easier to think of this thing as taking the area of the big triangle, which we know is 1, and subtracting off the two little unshaded triangles. So let's do it that way. Not the only way to approach the problem, but I think probably the easiest. So we take the total area of the big triangle, which is 1, and subtract off the probability that x is between 2 and 3. That'll be the little triangle on the left. And also then minus out the triangle on the right, which represents the probability that x is between 6.5 and that should say 5.5 and 6. Okay, we'll fix that in a little bit. Okay, so let's see if the rest of the calculations are correct here. So it's 1 minus, well, again, 1/2 base times height for the area of a triangle. So it's 1/2. 3.5 minus 2 is 1.5. That's going to be how far it is across the base of this first one. 1.5 across here. And how tall is it? Well, that's going to be the y value here at 3.5. And that's on the first curve, which was crossing here at 2. So it's x minus 2, 3.5 minus 2, times the slope of 1/6. Okay, well, that's 1.5 times 1/6 is 0.25. So this is 0.25 for the height. The base is 1.5, and then, of course, we always have a 1/2. So that gives us an area that's unshaded here of 0.1875. Now, if we look at the right-hand side, we get the area there of another triangle, very similar manner. 1/2 base times height. The base is 6 minus 5.5, so that's only a half for the width here, for the base, that's 0.5. And the height is negative 1/2, the slope, times 0.5 minus 6, which is a negative 0.5, times a negative 0.5 is a positive 0.25, and so that's the height here. So the height is 0.25, the base is 0.5, and then we multiply those together times 1/2, and we get 0.0625. So now we know we have 1 as the total area, the 0.1875 is the unshaded area on the left, and the unshaded little triangle on the right is 0.0625 for its area. Go ahead and do those two subtractions, and it does turn out to be exactly 0.75, or 3/4. So if you look at all these examples in this triangular distribution, I was able to use the fact that the area of a triangle is 1 for the big triangle, and then I was able to use just the area formula for a triangle, either to add them up or subtract off triangles, and somehow put this together to come up with the area that we need that represents the probability that we're trying to compute. Now, the next thing I want to do is look at the CDF. In general, CDFs start at 0, and the purple is the CDF here. It's on top of the red here on the left, and you can't really see it as well, but it's purple here as well. So 0 here, and then it continues and it goes up and levels out at 1. That is very typical of CDFs when we have a continuous distribution. They start at 0 and end at 1. And usually they'll do it in some kind of a smooth manner. In the there are some examples where it wasn't quite so smooth. In the discrete case, for example, in the discrete case, the CDF was kind of a stair-step thing. But in a continuous case, it's going to be connected. Okay, so, well, what does this have to do with anything? Well, the CDF, remember, is the cumulative density function. It's the accumulated probability of that point. So wherever I've got my cursor right at the moment, okay, I have an area, I have a y value of 0.41 where I am right at the moment. So that means the probability that x is less than or equal to whatever that x value is down there for that point will be 0.41, and that's also the shaded area. So that shaded area under the PDF is a probability. That is a y value on the CDF. So PDF, areas of probabilities, CDF, y values of probabilities. PDF always has positive or zero values. CDF always starts at 0 and ends at 1. And always must completely increase the entire time. Next, here we've gone out a little farther, okay, and we've done the same sort of thing. We've just gone out a little farther here and seen that we picked up more probability. So as we move this point to the right, we're going up on we're going to the right on the CDF curve, but it's also going up, so it's increasing, and we're picking up more and more probability, which means down on the PDF curve, we're picking up more and more area. At this point, we have 94% of the area behind us. Notice that the CDF does level off at 1 eventually. Now, what about the mean and median of a triangular distribution? Let's take a look at this. It turns out that the mode you already know, right? The mode is the x value that goes with this highest point. The median, we know, is an x value that gives us a probability of being less than that median is always exactly 0.5. So anytime you have the graph of a CDF and you want to find the median, we just graph this horizontal line here at y equals 0.5, find where that crosses the CDF, and bring it straight down and find that x that goes with it. So we just calculate the intersection of those two, and that x value is the value of our median. Of course, what does that have to do with the CDF? Well, that is the CDF. How does it have to do with the PDF? The PDF, then, the area to the left of that one, that would be a triangle in this case, has an area of, well, 1/2. Because in general, the areas to the left of a value on the PDF is exactly the same as the output or y value on the CDF. Now, the mean is a little harder to show why this is true, but I did a bunch of calculations, and it turns out that when the dust settles, we have a nice little formula for the mean. The mean is just the average of the A and the B and the mode. So it's A plus B plus mode divided by 3. And at the moment, the one you're looking at here has a mean of 5.51. Now remember, a mean is a balance point. If this triangular distribution here had some, was filled out with solid area, then we could put a balance point right here at the mean, and it would balance out. Now, this one is skewed to the left. Remember, when we say skewed to the left, that means we have a longer tail out to the left side. And notice that gives us an order here. The mean is less than the median, which is in turn less than the mode in this particular example. So usually, well, just in general, if we have a skewed to the left distribution, the mean is less than the median. Let's look at one where it's skewed to the right. This one's skewed to the right, and notice the mode, mean, and median sort of switch order, so the mode is less than the median, which is less than the mean. That gives you a little introduction to triangular distributions. So what I'm going to do also while I'm here is we're going to look a little bit at this Geometry Sketchpad sketch. Notice that this particular sketch is a triangular distribution, and I give it by parameter by typing in these boxes, the A and the B. So right now we're going between 2 and 9. A is 2 here, B is 9 here. The mode I can change by sliding anywhere from A to B along this curve here. Notice that the height of this triangle does not change. It does not depend on the value of the mode what the height is. The height is always 1 over B minus A. Now that height, of course, will change if I change this to something, say, smaller, like a 6. When we make the base smaller, we make the height bigger. I can make this even smaller still by making this 2.5, bringing that in some more. If I want the height to be shorter, then I need to make that base bigger, like maybe taking that all the way out to 10. But we do this in such a way that what happens? Well, the area under that triangle always stays 1. That's a characteristic of the graph or the formula or table or whatever for a continuous CDF. Okay, let's see what else we can see here. If you push on this button, it will show you some basic formulas, including the area formulas for the 2 lines that make this thing up. This one also shows us the CDF. And notice what happens if I change. So, notice that what happens here again, we can see the height is 0.5, and that comes down. Where that comes down here is the median. And you can see no matter where I put the mode, there is the median. Also, we can see the mean going. Notice that again, if it's really skewed to the right, the mode's over here, then the median, then the mean. If I'm on the other side, the other way around, and there is a point right in the middle when it's symmetric where the mean, median, and the mode are all the same value. Okay, and when that happens, then we have a symmetric distribution. Okay, so then it's this half is halfway between the 1 at the top and 0 at the bottom, but also we're halfway between the A and the B here as well when we have a symmetric distribution. We skew this a little, it brings all 3 measures to the left or all 3 to the right here. Okay, let's look at one more thing. If we look at our CDF here, we can look at, let's see, here it is. Here's a point. And notice that as this point moves to the right, we're picking up more and more area as we go to the right, approaching totally an area of 1 at the end. So it starts with an area of 0, picks up more and more area as we go to the right. And the area here that we have shaded is the same as the y value that we have here. So for example, right now we're at 0.8, and it goes on up. Another thing we can do with this, if we hide some of these things, let's see, let's hide that area. Well, we have some areas we can show. So this area here allows me to do areas to the left of the median, and it does compute the probability of the area, which is the probability here. And I have this worked out so that if we change the scale of the graph, that's adjusted here as well And so we can adjust the scale if we'd like to. But we can find that area. That's the probability. Here's an area E, and E always goes right to the median, and then you can go from there. F always starts at the median and it goes to the right. Area G is always to the right of the median. It could be the whole thing to the right or only part of it. And then also area H is on both sides of the median. And so one of these slides, this one. And so you can go as far as you want on this side and as far as you want on this side, but it has to be to the right or on the median there. And so those are some different areas we can look at and look at sort of the different cases, the different scenarios. So this sketch, of course, has the same things I've shown you earlier for uniform distribution and now for triangular distribution. And that gives you a good introduction to triangular distribution. So hopefully by looking at uniform and triangular distributions, we now have a good idea of the geometry of what's going on, the idea of the connection between the PDF and the CDF, okay, so that probabilities here add up, okay, as we raise that up the go to the right. And so the areas under the CDF are the y-values on the areas under the PDF are the y-values on the CDF. We also saw an idea of what's meant by the mode, the median, the mean. We got a little bit of idea about skewness and symmetry. And we also get this basic idea that what we want to do is compute areas for probabilities if we're looking at the PDF, and we want to look at y-values for probabilities if we're looking at the CDF. Okay, there's an introduction to triangular distributions.